Hello, dear students, kids, and who they are with the kids, specifically from the rural India. Konkan. Oh. Why you all are not with the Rubik cubes? Till the question still stays. You should be with the Rubik cubes. As in one man, he said, not everybody will make a choice, but always you will be in a search with a person who will make that particular choice. Every of the food has to be served in the beginning. Let them make a choice. Keep a watch on them. See who makes the choice. And that will be the one who's going to move on with everything what we have. So today is 11th standard refraction of light. I'll try to make a sense with the refraction of light, hyperrefraction, which comes from Professor Mohan Apte. Kadhi. Let's see how it goes. Hyperrefraction was a good concept. I don't know who you all are. Still trying to wonder what you all have on your mind. The refraction of light, 10 standards already what we know is a sine of ratio of sine of angle of incidence to the sine of angle of refraction. So let's say suppose if you have two medium separated by line and the light enters from one medium to the other medium, maybe like this. Like this. We'll say this is the medium A, that's the medium B. Light comes from the medium A. It goes to the medium B. A is called as an incident medium. B is called as a refracting medium. We'll say it's equal to sin I upon sin R. What is I and what is R? Of course, it's been already known. Angle of incident and angle of refraction. I'll try to entertain even the non-science people with a particular concept of hyperrefraction. Let's see how it goes. And there is a one particular problem concerned with an optical path. I'll try to have a discussion about it. Maybe that will be a little bit in an entertaining mode. So these are just a simple concept. Mr. Eugene said that it's a velocity in incident medium divided by velocity in refracting medium. If I say refractive index of any particular medium B with no medium said over here, then in that case, it's been taken as either air or the vacuum, and the refractive index of that particular medium with respect to the vacuum or the air, it's been termed as absolute refractive index. So I'll say this as V upon VB. This V has been termed as velocity of a light in the vacuum, and this has been termed as velocity of a light in the particular medium. So let's say suppose if I have the refractive index of Q with respect to P, then I should say it's absolute of refracting medium divided by absolute of incident medium, means mu of P. So how we write as C upon CQ divided by C upon CP. The CC's gets cancelled and CP upon CQ. We get this particular definition. That's the one more way to write the refractive index of any particular medium with respect to some other one in terms of their absolute refractive indices. This was not been discussed with my nephew. So he should take an attention with this. He should have he should make a note of this. I got English. So let's say suppose if you do the migration from a country to the country of whose currency is higher than us. Let's say the person goes from Q to P, India to America. Sin I upon sin. Expensive country means I think you have to spend more to get there less. You have to spend there more. Means it's somewhat like this. You come near to the normal. And if you go from India to Bhutan and all, India to Bhutan, so you'll go away from the normal. You can say that. That's some weird concepts. So now let's go with what they call as an optical path. What is the optical path? Let's say suppose if you walk through the water, गणपती विसर्जनला तुम्ही गेले आणि पाण्यामधनं चालत असाल, त्याचा रेजिस्टन्स म्यू आहे, जो हवेपेक्षा दुप्पट आहे, दुप्पट. Let's say suppose if you are walking through the water, which has got a resistance double than that of an air. So in a second, let's say suppose if you are completing a distance of 5 meters in the air, not 5 meters. Okay, let's say suppose if you are completing a distance of 5 meters in 10 seconds in air. So in 10 seconds, you will cover only 2.5 meters in this particular medium of water. ये पानी है, और ये आदमी जो दिख रहा है आपको, वो गणपति का विसर्जन करके खुशी से नाच नाच के समुद्र के पानी से आ रहा है, लेकिन फिर भी उसको ये पानी का रेजिस्टेंस महसूस हो रहा है, इसलिए वो कम डिस्टेंस चल सकेगा पानी में. तो अगर पानी में जिसका रेजिस्टेंस हवा से दुगुना है, लेट्स से सपोज इफ the resistance of the water is double than that of an air, in that he is walking 2.5 meters in 10 seconds. So in air, 10 seconds itself, he'll walk double the distance of this, which is 5 meters. So whatever the distance covered by light in any particular medium, whatever the distance is covered by light in any particular medium with a refractive index mu, let's say suppose if it is D, refractive index maybe I'll take it as a resistance offered by a particular medium for the flow of a water through the particular medium. So compared to that, the distance covered by light in the air will gonna be mu D. So mu D means comparative distance, whatever has been covered by light in the air, I'll call that as a optical path. An optical path difference compared to air of that particular medium, optical path difference, it is going to be mu D minus D. So all it comes D into bracket mu minus 1. Now the funny part is to realize this particular fact, it took me around 40 years of my life by referring many of the books and having a discussion. That's a sad part. But still, finally I get it. Now there is a particular problem. What was that problem? Let's say suppose if there is a lake, it has a water with a refractive index mu. There is a bird, he is in the air. It's not a bird, it's a fish. ये आकाश में एक पंछी उड़ रहा है, चिड़िया. वो पानी में एक मछली को देखती है, मछली जल की रानी है, जीवन उसका पानी है. So that bird observes the fish at a distance D, and fish observed the bird at a distance P. So I had to define the refractive index mu in terms of these two distances, D and P. There was some classical problem it was discussed when I was in a good state of life. So how I explain this now? Actual distance of bird from the surface of the water, I'll take it as X. And the distance of a fish, actual distance of a fish from the surface of the water deep inside, we'll take it as Y. So since this is the actual distance, means this is the distance in air, means suppose if the water would have not been there, the fish would have been observed at a distance Y. So now if the water is there, then it will be observed at a distance Y upon mu compared to air. And this distance, whenever the fish observed the bird, x, it will be observed as mu x. Means whenever you are observing from water to air, whatever the distance of an object from the surface is there, it will be a little bit improved. And whenever you're observing from air inside the water, the distance, whatever is there inside the water, it will be shrinked by amount of mu. So the two equations nicely they'll come as mu x plus y, mu x plus y is equal to P and x plus mu y. Mu y upon mu, sorry, x plus y upon mu is equal to q. So I'll just multiply mu x plus y is equal to mu q. So I have mu x plus y is equal to p, mu x plus y is equal to mu q. I'll just divide the two equations one by other. So mu x plus y divided by mu x plus y is equal to p upon mu q. So this goes 1. So certainly mu will gonna be there as p upon q. At that time, I struggled a lot to get this solution by myself, and I felt pride and all, whatever. A good time. Now, this seems to be some classical problem. Never I was in a particular situation that I observed something from the swimming pool, that I observed some particular object from a swimming pool, which is outside the swimming pool, somewhat as this. But I wish really should happen someday, but I don't want to learn swimming. Forget it. Now, there is a classical problem that is called as hyperreflection. This is specifically meant for non-commerce people. Hyperreflection. I feel that this particular concept should be used in particular science fiction movies, some particular science fiction movies. Now, what the concept is, refraction of light, what we know that incident ray, normal, and the diffracted ray. So I, R, whatever are there. This has been taken from one of the book by Professor Mohan Apte, Mala Uttar Hawaii. It's hyperrefraction. I think this particular situation is there in some particular planet. It's maybe Mars or I don't know. Shukrala, आता English मध्ये काय म्हणतात मला माहिती नाही. But how the concept, this mu, as the mu increases, this refracted ray comes closer to the normal all the time. But then there'll be a situation. The mu is so bad that the refracted ray gets back on the other side of the normal. This is what they call as a hyperrefraction. So angle of refraction is more than 90 or whatever. This. So on some particular planet, the refractive index is of that kind. So because of that, what it happens? Let's say suppose there are railways like how we have on Earth, on the particular planet. Here is the Grant Road station, Grant Road. I'm standing on a Grant Road station, platform number 1. Here is Professor Pankaj. So prior to Grant Road, which station comes? Charni Road. Then prior to that, which station comes? Marine Lines. And then it's come Churchgate. So line of sight, maybe it will be like this. So maybe I'll be able to observe something near under the bridge or whatever. But of course, after that, the train takes turn. Otherwise, even the things would have been in a straight line. These things won't be visible because the Earth is not flat. It is curved as this. So these stations will be somewhere over here, and they won't be seen. But some strange fact, it happens because of the hyperrefraction. Now, I really do not have any idea how this happens because of the hyperrefraction. I'm not a particle physicist. I am not concerned with lepton, proton, muon, gluon, tachyons, gravions, and all. Blah, blah, blah. But optics seems to be the most interesting branch. What it comes, optics. So what is because of the hyperrefraction? I really do not have any idea why it happens, but it happens something as this. These stations, whatever they are, they're visible now on the. I'll say this. This is the what Grant Road station. This is bridge. No, this is Marine Lines, and this is Charni Road. No, this is Charni Road. This is Marine Lines, and that is Churchgate. Churchgate च्या नंतर इकडे कुठेतरी मंत्रालय असेल. त्याच्या पुढे कुलाब असेल, कफ पर्ड असेल, अफगाण चर्च असेल, Afghan, and maybe I'll say later on there'll be Kendriya Vidyalaya school, and that must be the end. But let's say suppose if I'm standing over here on that particular planet, and the same constructions, I mean the construction of the planet is somewhat as same as this. Means I mean as like what it's there on the earth. And if I'm standing at the Grand Road station as how I look, so things will gonna be what? I'll try to elaborate. Because of that, no matter the stations will be on a flat line, but the rays of light will make this particular phenomenon happens, what they call as an hyperrefraction. And all those stations will be available right next to me, in front of me, as this. I mean to say, as it is, I'm standing in a bowl, kadhai. kadhai दाखवलं तेवढ्यात. So this is Grant Road, that is Churni Road, that is Marine Lines, this will be Churchgate. So again, over here, the bowl will go like this. Just let it stay. I think there was some error. Okay, now it went. And the bowl will go on the other side also as this. So Grant Road, Bombay Central will be over here, and maybe on the other level, after Bombay Central, which station comes? Mahalakshmi and all. Means basically the scenario will be somewhat as this. There'll be a big bowl, kadai. Pankaj sir will be standing at the Grant Road over here for waiting for his train. Here there'll be Churni Road, Marine Lines, Churchgate, Mantralaya, and then Kendriya Vidyalaya. Finally will be at this happen. Kendriya Vidyalaya will be there. And here there will be Bombay Central, Mahalakshmi. Mahalakshmi nanta kudla station ate. So lower parade, upper parade, lower parade. Then it will go on like this. Borivali will be somewhere in the. Now, I don't know why it exactly it happens. Maybe some sort of a strange explanation will be there. Now, whoever they must be pursuing higher astronomy in their life, they should try to have the perfect explanation for the even lower standard peoples. I think that will be more entertaining. When I was doing that particular course, I tried to ask about how to fix the distances of the distant stars by using the brightness of the sun. That professor, I think he made me fool out of all. And he didn't explain everything. There are some other methods available even to find the distances and all. But he said that in the beginning, because of the brightness of the stars, you can measure the distances of the other star. Means by knowing the distance and the brightness of a known star, you can find the distances of other stars whose brightness is known. But that was a little bit confusing. He said that logarithmic rule like decibels and all, it has been followed with even brightness. But brightness, it decreases along with the distances. So I don't know how the things are related. So suppose somebody is knowing about this particular fact about how to find the distances of the distant stars by using the brightness, well, please get back. I'll be waiting for the explanation. Refraction of light, what refraction of light? Rest of the other things always to be understood and to be learned and to be referred and all whatever. But this was the one good part was given by Miss Professor Mohan Apte, which I had to put it next to you. Thank you very much. Thank you. Thank you. God.